So here's something worth thinking about as you settle in tonight. Every single thing around you right now, the pillow under your head, the walls of the room, the faint glow of whatever light might still be on, the air filling your lungs, all of it, every last bit of it, is obeying rules. Not suggestions, not guidelines, but deep, unwavering rules that have held true since before the earth existed, since before the sun ignited, since before there were galaxies to hang in the dark. And the story of how we figured out those rules, how human beings went from staring at the sky in total bewilderment to writing down equations that could predict the behavior of particles smaller than atoms. That story is one of the greatest adventures our species has ever been on. It's messy and beautiful and full of wrong turns and stubborn geniuses and lucky accidents, and it stretches back thousands of years. So let's start there. Let's go all the way back. Picture the ancient world. Not ancient the way we casually say it, but truly ancient. We're talking about the Eastern Mediterranean, maybe 2,500 years before the Common Era, give or take. Civilizations in Mesopotamia, in Egypt, in what's now Iraq and the Nile Delta. These were people who built enormous things. The pyramids at Giza were already standing by around 2,500 BCE, and if you think about what that means in practical terms, it's staggering. They moved blocks of limestone weighing 2.5 tons each, some of them much more, and stacked them with a precision that modern surveyors still find impressive. The base of the Great Pyramid is level to within about 2 centimeters across a footprint of over 13 acres. That's not luck. That's engineering. And engineering, even at that early stage, requires some understanding of how the physical world behaves. But here's the thing. Those early builders weren't doing physics, not the way we'd recognize it. They were doing something more like accumulated craft knowledge. They knew that if you put a ramp at a certain angle, you could drag stones up it. They knew that a plumb line hangs straight down and that water finds its own level. They knew these things because generations of trial and error had taught them. What they didn't have, and what nobody had yet, was a framework for asking why. Why does the plumb line hang straight? Why does water level itself? What's actually going on underneath the surface of things? That question, the why question, is where physics really begins. And it begins, as far as we can trace it, with the Greeks. Now, the Greeks get a lot of credit in the history of science, and sometimes people push back on that, rightly pointing out that knowledge was flourishing in China, in India, in the Islamic world, in places that European-centered histories have often overlooked. And we'll get to those contributions because they're essential. But the particular move that the Greeks made, starting around the 6th century, BCE, was genuinely distinctive. They started trying to explain natural phenomena not through mythology, not through the will of the gods, but through reason, through argument, through logic and observation. The person usually credited with kicking this off is Thales of Miletus. He lived around 624 to about 546 BCE in what's now the western coast of Turkey. And Thales is a fascinating character. He was a merchant, a traveler, probably spent time in Egypt and Babylon, and he came back with this radical idea. He proposed that everything in the world, all matter, all substance, was ultimately made of one thing: water. Now, that sounds quaint to us, almost childish. But think about what he was actually doing. He was saying that the universe isn't arbitrary, isn't a playground of capricious gods. It has an underlying unity. There's a substance, a principle, beneath the apparent chaos of the world, and if you could understand that principle, you could understand everything. That's a physics instinct. That's the same instinct that drives people today to look for a theory of everything, a single framework that unifies all the forces of nature. Thales was wrong about water, obviously, but the impulse, the audacity of saying the universe is comprehensible and unified, that was revolutionary. And he wasn't alone. After Thales came a whole lineage of thinkers in that same region, the so-called pre-Socratic philosophers, each one pushing the idea further. Anaximander, who was probably Thales' student, said no, the fundamental substance isn't water, it's something more abstract, something he called the apeiron, the boundless, or the indefinite. He was groping toward the idea that the basic stuff of reality might not be any familiar material at all. Anaximenes said it was air, and that everything else was just air compressed or rarefied to different degrees. Again, wrong in the specifics, but the concept that one substance could transform into different states depending on how it was arranged or compressed, that's not a million miles from how we think about phases of matter today. And then there's Heraclitus, over in Ephesus, around 500 BCE, who said the fundamental element was fire and that everything is in constant flux. You cannot step into the same river twice, he supposedly said. The universe isn't a static thing. It's process, it's change, it's transformation. And honestly, modern physics would agree with him more than you might expect. At the quantum level, nothing is truly still. Everything vibrates, fluctuates, shifts. But the one who really set the stage for what physics would eventually become was someone else entirely. Democritus, born around 460 BCE in Abdera in northern Greece. Democritus, along with his teacher Leucippus, proposed something breathtaking. He said that if you took any piece of matter and kept cutting it in half, and then in half again and again, eventually you'd reach a piece so small it couldn't be cut anymore. He called these pieces atomos, which literally means uncuttable. Atoms. He said the entire universe was made of atoms moving through empty space, void, colliding and combining in different patterns to create everything we see. Rocks, water, air, flesh, stars, all of it, just atoms and void. Think about that for a second. 2,400 years ago, a guy sitting in a Greek colony with no microscope, no particle accelerator, no instruments of any kind beyond his own mind, reasoned his way to an idea that is, in its broad strokes, correct. We now know that atoms aren't actually uncuttable, that they have internal structure, protons and neutrons and electrons and quarks beneath those. But the core insight, that matter is made of tiny discrete particles too small to see, moving and interacting according to rules, that insight is the foundation of modern physics and chemistry. Democritus got there through pure thought. It's one of the most impressive intellectual achievements in human history, and it happened before Socrates had even started annoying people in the Athenian marketplace. Now, you might wonder, if Democritus had this brilliant idea so early, why didn't physics just take off from there? Why did it take another 2,000 years before anyone really built on it? And the answer has a lot to do with one man who, for better and worse, cast a shadow over Western science that lasted for almost 2 millennia. Aristotle. Aristotle was born in 384 BCE in Stagira, in northern Greece, and he was, by any measure, one of the most influential thinkers who ever lived. He studied under Plato, tutored Alexander the Great, and wrote about everything: logic, ethics, politics, biology, poetry, metaphysics, and yes, what we'd now call physics. His book on the subject is literally called Physics, and Aristotle was brilliant. His observations of biological organisms were so detailed and accurate that Darwin himself praised them 2,000 years later. His system of logic dominated Western thought for centuries. But when it came to the physical behavior of matter and motion, Aristotle got some very important things wrong. And because of his enormous authority, those wrong ideas stuck around for a very, very long time. Here's what Aristotle thought about motion. He divided it into two kinds: natural motion and violent motion. Natural motion was what things did on their own, left to themselves. Heavy things, like rocks, naturally moved downward toward the center of the earth, because that was their natural place. Light things, like fire and smoke, naturally moved upward. Celestial objects, the stars and planets, naturally moved in perfect circles, because circles were the most perfect shape, and the heavens were the realm of perfection. Violent motion was anything that wasn't natural, anything caused by an external push or pull. You throw a rock, that's violent motion. A cart pulled by a horse, violent motion. And here's the key assumption, the one that caused so much trouble later. Aristotle believed that violent motion required a continuous force. If you stopped pushing something, it would stop moving. Immediately. That was his claim. Now you're lying there, and you might already sense the problem, because you've thrown a ball before. You let go of it, and it keeps going. Your hand isn't touching it anymore, but it sails through the air. How did Aristotle explain that? He said the air itself was doing the pushing. As the object moved forward, it created a sort of vacuum behind it, and the air rushed in to fill that vacuum, pushing the object along. It's an ingenious explanation, honestly. It's wrong, but it's clever. And for a long time, people accepted it, because Aristotle said it, and Aristotle was Aristotle. He also believed that heavier objects fall faster than lighter ones. Twice as heavy, twice as fast. That seems intuitive, right? A boulder feels like it should fall faster than a pebble. But it's not true. At least not in the way he meant it. In a vacuum, a feather and a bowling ball fall at exactly the same rate. We know this now. The Apollo 15 astronauts actually demonstrated it on the moon in 1971, dropping a hammer and a feather in the lunar vacuum and watching them hit the ground at the same instant. But Aristotle didn't have a vacuum to experiment in, and his reasoning, based on everyday observation in air where feathers do float and boulders do thud, seemed perfectly sensible. And this is worth pausing on, because it tells you something important about the history of physics. Common sense is often the enemy of understanding. The universe doesn't owe us intuitive behavior. It does what it does, and our job is to figure out the actual rules, not the ones that feel right. Aristotle was a genius who trusted his intuition, and his intuition led him astray on some of the most fundamental questions about how things move. It would take nearly 2,000 years for someone to come along and say, actually, let's stop assuming and start measuring. But we're getting ahead of ourselves. Before we get to that revolution, there's another figure from the ancient world who deserves real attention. Someone who did something that Aristotle and the other philosophers mostly didn't do. He got his hands dirty. He built things. He tested things. He calculated things with a rigor and precision that wouldn't be matched for centuries. Archimedes of Syracuse. Archimedes was born around 287 BCE in Syracuse, on the island of Sicily, which was then a Greek colony. And if Democritus gave us the idea of atoms through pure reason, Archimedes gave us something equally important. He showed that you could use mathematics to describe physical reality with exactness. Not approximately, not poetically, but precisely. He worked out the principle of the lever and he expressed it as a mathematical law. A weight on one side of a fulcrum balances a weight on the other side when the products of weight and distance are equal. Simple, elegant, and testable. He reportedly said, "Give me a place to stand, and I shall move the earth," which is a beautiful way of saying that the lever, properly understood, gives you mechanical advantage without limit. He also figured out the principle of buoyancy, the famous story about the golden crown. King Hero of Syracuse had commissioned a gold crown and suspected the goldsmith had cheated him by mixing in cheaper silver. He asked Archimedes to figure it out without damaging the crown. And the story goes that Archimedes was getting into a bath, noticed the water level rise as his body displaced it, and realized that he could measure the volume of the crown by how much water it displaced. Compare that volume to the weight, and you'd know the density. If the density matched pure gold, the crown was genuine. If it was less dense, silver had been mixed in. He supposedly leapt from the bath and ran through the streets shouting, "Eureka!" which means, "I have found it." The story is probably embellished, maybe even apocryphal, but the principle is real and bears his name, Archimedes' principle. Any object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. That's why ships float. That's why you feel lighter in a swimming pool. That's why hot air balloons rise. One principle, figured out in a bathtub in Sicily, and it governs everything from submarine design to the behavior of magma beneath the Earth's crust. What made Archimedes different from the philosophers was that he insisted on mathematical proof tied to physical reality. He didn't just argue that levers worked a certain way. He proved it geometrically. He didn't just observe that things float. He quantified the conditions under which they float, sink, or remain neutrally buoyant. He was, in a very real sense, the first physicist in the modern meaning of the word, someone who combines observation, experiment, and mathematical reasoning to uncover the laws of nature. And he did all this while also being a practical engineer of the highest order. During the Roman siege of Syracuse in 213 BCE, Archimedes designed war machines that held off the Roman fleet for months, giant cranes that could lift ships out of the water and drop them, catapults calibrated for different ranges. Whether or not he actually used mirrors to focus sunlight and set ships on fire, that story is more legend than fact, but the mechanical defenses were real enough that the Roman general Marcellus reportedly said he was fighting a one-man army. When Syracuse finally fell in 212 BCE, Archimedes was killed by a Roman soldier, supposedly while working on a mathematical diagram in the sand. His last words, according to tradition, were, "Do not disturb my circles." So by the time we reach the end of the ancient Greek era, we have these incredible threads laid down. Democritus gave us atoms. Aristotle gave us a comprehensive but flawed framework for understanding motion and matter. Archimedes gave us the marriage of mathematics and physical law. And all around the Mediterranean and beyond, in Alexandria, in the great library that became the intellectual center of the ancient world, scholars were building on these ideas, refining them, arguing about them, translating them. But here's what's interesting about what happened next. As the Roman Empire rose and eventually fell, as Europe entered the period we sometimes call the early medieval era, much of this Greek knowledge didn't disappear. It migrated. It moved east and south into the Islamic world, where something remarkable was about to happen. In Baghdad, in Cairo, in Cordoba, scholars weren't just preserving Greek texts. They were extending them, correcting them, and in some cases, surpassing them entirely. And one of the people at the center of that story, a man whose contributions to physics are still underappreciated in the West, was working in a city on the banks of the Nile around the year 1000 CE, and his name was Ibn al-Haytham. And if you haven't heard of him, you're not alone, because for centuries, Western histories of science barely mentioned him. But this man, born in Basra around 965 CE, may have done more to establish the modern scientific method than anyone before Galileo, and his work on optics, on how light actually behaves, was so far ahead of its time that it shaped physics for the next 600 years. Now, let me set the scene for you, because the world Ibn al-Haytham lived in was extraordinary. The Islamic Golden Age, roughly the 8th through the 14th centuries, was one of the most intellectually productive periods in human history. And it wasn't an accident. The Abbasid caliphs in Baghdad had actively sponsored translation movements, hiring scholars to translate Greek, Persian, Indian, and Syriac texts into Arabic. There was a famous institution called the House of Wisdom, Beit al-Hikmah in Baghdad, and while historians debate exactly what it was, a library, a translation bureau, a research academy, probably all of those things at different times. The point is that there was institutional support for knowledge, patronage, funding, the idea that understanding the natural world was not just permitted, but encouraged, even celebrated. And so you had this incredible flowering. Scholars like al-Khwarizmi, whose name literally gives us the word algorithm, were inventing algebra. Al-Razi was writing medical encyclopedias. Al-Biruni was calculating the radius of the Earth to within about 15 kilometers of the modern value. This was not a culture that was merely storing Greek ideas in a vault. This was a culture that was doing new science. And into this world comes Ibn al-Haytham. He was, by most accounts, a polymath: mathematics, astronomy, philosophy, engineering. There's a famous story, and it may be partly legendary, that he claimed he could regulate the flooding of the Nile by building a dam. The Fatimid Caliph al-Hakim, who ruled Egypt at the time, heard about this boast and summoned Ibn al-Haytham to Cairo to make good on it. So Ibn al-Haytham traveled to Egypt, surveyed the Nile, and quickly realized the project was far beyond the engineering capabilities of the era. He couldn't do it. And this was a problem, because al-Hakim was not known for being a forgiving ruler. The story goes that Ibn al-Haytham feigned madness to avoid punishment and was placed under house arrest, where he remained for roughly a decade until al-Hakim's death in 1021. And here's the thing: that period of house arrest, that enforced solitude, may have been the most productive decade of his life, because it was during this time that he wrote his masterwork, the Kitab al-Manazir, the Book of Optics. Now, why does optics matter so much to the history of physics? Think about it this way. Light is how we perceive the world. It's the primary channel of information between reality and our brains. And yet, for over 1,000 years, nobody really understood how it worked. The Greeks had two competing theories. One, championed by thinkers like Euclid and Ptolemy, was called the emission theory. The idea that your eyes send out rays, like invisible feelers, that go out and touch objects and bring back information. You're literally reaching out with your vision. The other theory, closer to what Aristotle suggested, was that objects somehow alter the medium between themselves and the eye. Neither theory was quite right, and neither had been rigorously tested. Ibn al-Haytham did something radical. He said no, light travels from objects to the eye, not the other way around. Light comes from luminous sources like the sun or a flame. It bounces off objects, and it enters your eye. That's how you see. And he didn't just assert this, he proved it through experiments. He built dark chambers, what we'd now recognize as early versions of the camera obscura, and showed that light from a candle passing through a small hole into a dark room projects an inverted image on the opposite wall. He demonstrated that light travels in straight lines. He studied reflection and refraction systematically, measuring angles, varying conditions, recording results. This is experimental physics. This is the method. Form a hypothesis, design an experiment, observe what happens, revise your understanding based on the evidence. And he was doing it in Cairo around the year 1020, more than 600 years before Newton published his optics. Let that sink in for a moment. 600 years. And the Book of Optics wasn't some obscure manuscript that gathered dust. It was translated into Latin in the late 12th or early 13th century, where it was known as De Aspectibus, or Perspectiva, and it profoundly influenced European scholars like Roger Bacon, Vitello, and eventually Johannes Kepler. When Kepler finally worked out how the human eye focuses light onto the retina in the early 1600s, he was building directly on foundations that Ibn al-Haytham had laid. But here's what's really beautiful about Ibn al-Haytham's approach, and why it matters beyond just optics. He was explicit about the importance of skepticism and self-correction. He wrote that the seeker of truth is not one who studies the writings of the ancients and puts his trust in them, but rather the one who suspects his faith in them and questions what he gathers from them, submitting to argument and demonstration. That's not a paraphrase. That's remarkably close to his actual words. He was saying, don't just trust Aristotle because he's Aristotle. Test it. Check it. And if the evidence contradicts the authority, go with the evidence. That idea, which feels so natural to us now, was genuinely revolutionary. It's the beating heart of the scientific method. So the Islamic Golden Age gave physics not just specific results, though those were extraordinary, but a methodology, a way of working. And it preserved and transmitted the Greek legacy, enriched with new mathematics, new observations, new instruments, so that when European scholars eventually gained access to these texts, they weren't starting from scratch. They were inheriting a living tradition. Now, the transition of knowledge back into Europe is a story in itself, and it happened through several channels. One of the most important was medieval Spain, Al-Andalus, where Muslim, Christian, and Jewish scholars coexisted and collaborated, particularly in cities like Toledo. In the 12th century, a massive translation effort turned Arabic texts, including Arabic translations of Greek originals, into Latin. Gerard of Cremona, an Italian scholar who moved to Toledo specifically to find Ptolemy's Almagest, ended up translating over 70 works from Arabic to Latin, covering astronomy, mathematics, medicine, and natural philosophy. Through this pipeline, Aristotle's physics, enriched by Islamic commentary and critique, re-entered European intellectual life. And this brings us to the medieval European universities, which were just getting started. Bologna, Paris, Oxford. These institutions were founded in the 12th and 13th centuries, and they became the places where the recovered knowledge was taught, debated, and gradually transformed. Now, I want to be careful here, because there's an old narrative that says the medieval period was just a dark age of intellectual stagnation in Europe, and that's not really fair. It's true that the dominant framework was still Aristotelian, and it's true that theology constrained what questions could be asked. But within those constraints, some genuinely important physics was being done. Take the Oxford calculators, for instance. This was a group of scholars at Merton College, Oxford, in the 1320s and 1330s. People like Thomas Bradwardine, William Heytesbury, Richard Swineshead. They were working on the problem of motion, the same problem Aristotle had tackled, and they were making real progress. They distinguished between what we'd now call velocity and acceleration. They formulated the mean speed theorem, which says that a uniformly accelerating body covers the same distance as a body moving at constant speed, equal to the average of the initial and final velocities. That sounds dry when I state it like that, but think about what it means. They were mathematizing motion. They were taking something that Aristotle had described in qualitative, philosophical terms. Heavier things fall faster, objects need continuous force to keep moving, and they were turning it into precise mathematical relationships. And the mean speed theorem is correct. It's essentially what you derive from the equations of motion that every physics student learns today. They got there 300 years before Galileo. Around the same time, in Paris, a scholar named Jean Buridan was poking holes in Aristotle's theory of projectile motion. Remember Aristotle's problem. If you throw a ball, what keeps it moving after it leaves your hand? Aristotle had said the air somehow pushes it along, which never really made sense. Buridan proposed instead that the thrower imparts something to the object, a quality he called impetus that keeps it moving. The impetus gradually dissipates, which is why the object eventually slows down and stops. Now, impetus isn't quite the same as Newton's concept of inertia or momentum. It's not as clean, and Buridan still thought the impetus would naturally decay even without any opposing force. But it was a huge step in the right direction. It was saying that motion doesn't require continuous external pushing. Something internal to the object, acquired from the initial force, sustains the motion. That's a crack in the Aristotelian edifice, a significant one. And Buridan's student, Nicole Oresme, took things even further. Oresme, who eventually became the Bishop of Lisieux, was one of the most creative thinkers of the 14th century. He developed a graphical method for representing the mean speed theorem, essentially plotting velocity against time, which is something we do routinely now, but was genuinely novel then. He also argued, purely as a thought experiment, that it was simpler to assume the Earth rotates on its axis once a day than to assume the entire heavens revolve around the Earth. He didn't commit to this as physical truth. He ultimately deferred to Scripture. But the fact that he could articulate the argument, that he could see that the physics worked either way, shows how sophisticated the thinking had become. So by the late medieval period, the ground was being prepared, the tools were being sharpened, the questions were getting sharper too. But Aristotle's framework was still standing, battered but intact, held up partly by its own internal logic and partly by the authority of the Church, which had adopted Aristotelian natural philosophy as compatible with Christian theology. Thomas Aquinas had woven Aristotle so thoroughly into Catholic thought that challenging Aristotle's physics started to feel like challenging the faith itself. And that created a tension, a pressure that was building slowly, like stress accumulating in a structure that hasn't been designed to handle the load. What was needed was someone willing to actually go outside and check. To stop arguing about what Aristotle said objects should do and start watching what objects actually do. To measure, to time things, to let the world speak for itself. And that someone, the person who would finally and irrevocably crack the Aristotelian framework wide open, was born in Pisa in 1564, the same year that Michelangelo died and Shakespeare was born, as if history had a sense of dramatic timing. His name was Galileo Galilei, and the story of how he changed everything begins, of all places, in a cathedral with a swinging lamp and a young man's restless curiosity. Galileo was maybe 19 or 20 years old, sitting in the Cathedral of Pisa, and the story goes that he noticed one of the great oil lamps overhead had been set swinging, probably by a sacristan who'd pulled it aside to light it. And Galileo, being Galileo, didn't just watch it swing. He timed it. He used his own pulse, pressing his fingers to his wrist and counting beats as the lamp arced back and forth, back and forth. And here's what he noticed, something that would have surprised most people at the time. Whether the lamp was swinging in a wide arc or a narrow one, the time it took to complete each swing seemed to be the same. A big swing and a small swing took roughly the same number of heartbeats. The amplitude changed, but the period didn't. Or at least, it didn't change much. Now, this observation, that a pendulum's period is approximately independent of its amplitude, what we call isochronism, isn't perfectly true for large swings, but for small and moderate ones, it's remarkably close. And Galileo latched onto it. He went home and started experimenting with pendulums, hanging weights from strings of different lengths, timing them, comparing. He found that the thing that really determined the period wasn't how far the pendulum swung, or how heavy the weight was, but how long the string was. A longer string meant a slower swing. And this was the kind of result that Galileo loved. Clean, measurable, mathematical. It was physics you could pin down with numbers, not philosophy you could argue about in Latin. But let's step back for a moment and think about who Galileo actually was at this point. He wasn't yet the famous rebel of science. He was the eldest son of Vincenzo Galilei, a musician and music theorist from Florence. And that detail matters more than you might expect. Vincenzo was the kind of person who challenged authority in his own field. He argued against the rigid mathematical theories of musical harmony that had been handed down from the ancients, insisting that the ear, not abstract ratios, should be the final judge of what sounded good. He ran experiments with strings of different tensions and materials to test his ideas. So Galileo grew up in a household where questioning received wisdom wasn't just tolerated. It was dinner conversation, where you tested things instead of just accepting what the old book said. Galileo enrolled at the University of Pisa to study medicine. That was his father's practical plan for him. But he was drawn irresistibly to mathematics and natural philosophy. He eventually left without a degree, which was not exactly a recipe for career success in 16th century Italy. But he was brilliant and persistent, and frankly, kind of combative. He had a talent for making enemies, which would matter enormously later. He also had a talent for building things, for designing experiments, for seeing through to the essential question hiding inside a complicated situation. And the essential question that consumed him, the one that would define the first great revolution in physics, was this: how do things actually move? Think about what a radical question that was. For nearly 2,000 years, the answer had been Aristotle's answer. Heavy things fall, because they're seeking their natural place at the center of the universe. Heavier things fall faster than lighter things. Objects in motion need a continuous force to keep them moving. These ideas felt intuitive. They matched a kind of common sense experience of the world. If you push a cart and stop pushing, the cart stops. If you drop a cannonball and a musket ball from the same height, the cannonball seems like it should hit first. But Galileo wasn't satisfied with common sense. He wanted measurements. And this is where the famous story of the Leaning Tower of Pisa comes in. You've probably heard some version of it. Galileo climbing to the top of the tower and dropping two balls of different weights to show they hit the ground at the same time, proving Aristotle wrong in front of a crowd of astonished professors. It's a wonderful image, and it captures the spirit of what Galileo was doing, but most historians think it probably didn't happen quite that way. The story comes mainly from a biography written by Galileo's student, Vincenzo Viviani, after Galileo's death, and Viviani had a tendency to polish things up. What we do know is that Galileo thought deeply about falling bodies and came to the conclusion, through a combination of thought experiments and actual experiments, that Aristotle was wrong. All objects, regardless of weight, fall at the same rate in the absence of air resistance. Here's the thought experiment, and it's beautiful in its simplicity. Imagine you have a heavy stone and a light stone. Aristotle says the heavy one falls faster. Okay, now tie them together with a string. What happens? Well, by Aristotle's logic, the light stone should slow down the heavy stone, because it naturally falls more slowly. It should act as a drag. So the combined object should fall at some intermediate speed, slower than the heavy stone alone. But wait, the combined object is heavier than either stone individually. So by Aristotle's own rule, it should fall faster than either one. You've got a contradiction. The same object should fall both faster and slower. The only way out of the contradiction is to conclude that weight doesn't determine the speed of fall at all. Everything falls at the same rate. That's the kind of argument that makes you sit back and think, how did nobody see this for 2,000 years? And the answer is partly that people did see problems with Aristotle. Remember Buridan and his impetus theory. Remember the Oxford calculators working out the mathematics of acceleration. But nobody had quite put it all together with the clarity and the stubbornness and the experimental rigor that Galileo brought. He didn't just argue that Aristotle was wrong. He replaced Aristotle's framework with something better, something quantitative. And here's how he did it. Galileo realized that studying free fall directly was impractical. Objects fall too fast to time accurately with the technology he had. So he did something clever. He slowed things down. He rolled bronze balls down inclined planes, smooth wooden ramps that he'd polished and lined with parchment. By tilting the ramp at a gentle angle, he could make gravity's effect gradual enough to measure. He timed the balls using a water clock, essentially a jug with a small hole in the bottom, collecting the water that flowed out during each run and weighing it to determine elapsed time. It sounds crude, but it was remarkably precise for the era, and what he found was extraordinary. The distance a ball traveled down the ramp was proportional to the square of the time elapsed. Double the time, and the ball covers 4 times the distance. Triple the time, 9 times the distance. This is the signature of constant acceleration. The ball isn't just moving, it's speeding up at a steady rate, and this relationship held regardless of the weight of the ball. Galileo had discovered the law of uniform acceleration due to gravity, and he'd done it not by philosophical argument, but by measurement, by letting the world speak for itself, exactly as we said someone needed to do. Now there's something deeply important happening here that goes beyond the specific result about falling bodies. Galileo was establishing a method. He was showing that the way to understand nature is to isolate a phenomenon, strip away the complications, design an experiment that lets you measure the essential variables, and then describe the result mathematically. This is the birth of what we now call experimental physics, and it's hard to overstate how revolutionary it was. Before Galileo, natural philosophy was largely about categorizing and explaining in qualitative terms. This happens because of that principle. This substance has this essential nature. After Galileo, physics became about measuring and calculating, about equations. He also developed ideas about inertia that would prove crucial for everything that came after. Aristotle had said that an object in motion needs a continuous force to keep it moving. Galileo argued the opposite, that an object in motion on a frictionless surface would continue moving forever in a straight line without any force at all. Force isn't what keeps things moving. Force is what changes motion. This was a profound inversion of intuition, and Galileo arrived at it partly through another beautiful thought experiment. Imagine a ball rolling down one inclined plane and up another. It will rise to approximately the same height it started from, regardless of the angle of the second plane. Now make the second plane less and less steep. The ball has to roll farther and farther to reach its original height, and if the second plane is perfectly horizontal, the ball never reaches its original height, so it just keeps rolling forever. Inertia, motion without force, the idea that would become Newton's first law. But Galileo's most consequential and most dangerous work wasn't about falling balls or pendulums. It was about the sky. In 1609, he heard about a new invention from the Netherlands, a device that used lenses to make distant objects appear closer, a spyglass. Within months, Galileo had built his own version, improved it significantly, and done something that nobody had thought to do systematically before. He pointed it upward. He looked at the moon and saw that it wasn't a perfect, smooth celestial sphere as Aristotle had taught. It had mountains and craters and valleys. It looked, frankly, like Earth. He looked at Jupiter and discovered 4 tiny points of light orbiting it, moons. Other worlds with their own satellites, which meant that not everything in the heavens revolved around the Earth. He observed the phases of Venus and found that they matched what you'd expect if Venus orbited the Sun, not the Earth. He saw that the Milky Way wasn't a smear of celestial light, but was made up of countless individual stars, far more than anyone had imagined. Each of these observations was a crack in the Aristotelian Ptolemaic universe, and Galileo, never one to keep quiet, published his findings in a little book called Sidereus Nuncius, the Starry Messenger, in 1610, and it made him famous across Europe almost overnight. He was appointed chief mathematician and philosopher to the Grand Duke of Tuscany. He was celebrated, consulted, admired. But he was also making powerful enemies, because every observation he reported was another blow to the worldview that the Church had built its cosmology around. And Galileo, with his sharp tongue and his impatience for fools, wasn't exactly diplomatic about it. The conflict built slowly. In 1616, the Church formally declared that the idea of the Earth moving around the sun was foolish and absurd in philosophy, and formally heretical. Galileo was warned not to hold or defend the Copernican view. He complied, mostly for a while. But in 1632, he published his masterwork, the dialogue concerning the 2 chief world systems, which was structured as a conversation between 3 characters debating the merits of the Ptolemaic and Copernican systems. Galileo presented it as a balanced discussion, but it was about as balanced as a trial where the defense attorney is also the judge. The character defending Aristotle and Ptolemy was named Simplicio, literally, the simpleton, and Pope Urban VIII, who had once been Galileo's friend and supporter, believed that some of his own arguments had been put into Simplicio's mouth. The Pope was furious. In 1633, Galileo was summoned before the Inquisition in Rome. He was 69 years old, in poor health, and facing the full institutional weight of the most powerful religious organization in Europe. After a trial that was more political than theological, he was found vehemently suspect of heresy, forced to recant his support for the Copernican system, and sentenced to house arrest for the remainder of his life. The famous story that he muttered, "Eppur si muove," and yet it moves, under his breath after recanting is almost certainly legend, but it captures something true about the man. He never really stopped believing what the evidence told him. And here's the thing that's sometimes overlooked in the drama of the trial. During those final years of house arrest, blind and aging in his villa near Florence, Galileo wrote what many consider his most important scientific work, the discourses and mathematical demonstrations relating to two new sciences, published in 1638. This is where he laid out his mature thinking on mechanics and the strength of materials, the work on falling bodies and projectile motion, and the mathematics of acceleration that we've been talking about. He couldn't publish it in Italy. The Inquisition had banned his works, so it was smuggled out to the Protestant Netherlands and published by the Elsevier Press in Leiden. The book that founded modern physics was, in a very real sense, contraband. Galileo died in January 1642, still under house arrest, and later that same year. Well, it depends on which calendar you use, because England was still on the old Julian calendar. But on Christmas Day, 1642, in a farmhouse in Lincolnshire, England, a premature baby was born so small that his mother said he could have fit inside a quart mug. Nobody expected him to survive the week. His name was Isaac Newton, and what he would do with the foundation Galileo had laid would change everything. Not just physics, everything. So let's talk about this boy. Isaac Newton grew up in circumstances that were, honestly, pretty rough emotionally. His father, also named Isaac, died 3 months before he was born. His mother, Hannah, remarried when Newton was 3 years old, and she moved in with her new husband, a wealthy clergyman named Barnabas Smith, and left young Isaac behind to be raised by his maternal grandmother. Think about that, a toddler, essentially abandoned by his surviving parent. Newton later wrote in a list of his sins, he actually kept a list, that he had threatened to burn his mother and stepfather alive in their house. He was maybe 12 when he wrote that. Whatever else you want to say about Newton, he carried a deep, burning anger his whole life, a ferocious need to be right, to be recognized, to dominate. And that psychological fuel, as uncomfortable as it is to say, drove some of the most extraordinary intellectual achievements in human history. He was sent to the King's School in Grantham, where he was apparently a mediocre student at first, but eventually rose to the top. His mother pulled him out of school as a teenager to manage the family farm, and he was absolutely terrible at it. Sheep wandered off. Fences went unrepaired. He'd be found under a tree reading a book while the cattle trampled the neighbor's crops. Eventually, his uncle and his schoolmaster convinced Hannah to send him to Cambridge, to Trinity College, which he entered in 1661 as a sub-sizar, essentially a poor student who paid his way by serving wealthier ones. He waited tables, emptied chamber pots, ran errands. Newton at Cambridge, serving drinks to aristocrats' sons. It's an image worth holding in your mind. Now, the curriculum at Cambridge in the 1660s was still largely Aristotelian. They were teaching the old natural philosophy, the old logic. But Newton, on his own, started reading the moderns. He got hold of Descartes, who had proposed a mechanical philosophy of the universe, The idea that everything could be explained by matter in motion, by particles pushing against each other, no mysterious forces needed. He read Kepler's work on planetary motion. He read Galileo. And he read the mathematics, particularly Descartes' analytical geometry, which showed how you could translate geometric shapes into algebraic equations. Newton devoured all of this outside the official curriculum, filling notebooks with his own thoughts and extensions. He was, in the most literal sense, self-taught in the subjects that would make him immortal. And then something remarkable happened. In 1665, plague came to England. The Great Plague swept through London and into the countryside, and Cambridge closed. Students were sent home. Newton went back to Woolsthorpe Manor, the family farmhouse in Lincolnshire, and spent roughly 18 months there during 1665 and 1666. And in that period, he was 24 years old. He essentially invented calculus, discovered the composition of white light, and began formulating his theory of universal gravitation. Those 18 months are sometimes called the annus mirabilis, the miracle year, though it was really more like a miracle year and a half. There is nothing else quite like it in the history of science. One person, barely out of his student years, alone in a farmhouse during a pandemic, laying the foundations for 3 separate revolutions. Let's take them one at a time, because each one matters, and each one connects to what came before. Start with calculus, which Newton called his method of fluxions. Here's the problem he was trying to solve, and it's a problem that had been lurking in physics since Galileo. Galileo had shown that objects accelerate. Their velocity changes over time. He could describe the relationship between distance and time for a falling body. But the mathematical tools available to him were essentially static. Geometry could describe shapes. Algebra could solve equations. But the natural world is in constant flux. Things move, they speed up, they slow down. Forces vary from moment to moment. What Newton needed, what physics needed, was a mathematics of change itself. A way to talk precisely about quantities that are continuously varying. And that's what calculus is. Think of it this way. If you're driving a car and I ask you your speed, you might glance at the speedometer and say 60 miles per hour. But what does that actually mean? It means that if you kept going at exactly this rate, you'd cover 60 miles in 1 hour. But you're not going to keep going at exactly this rate. You're going to speed up, slow down, hit traffic, coast downhill. Your speed is changing every instant. So what is your speed at one specific instant? That's a surprisingly tricky question, because speed is distance divided by time, and at a single instant, no time passes and no distance is covered. 0 divided by 0. Meaningless. What Newton figured out, and Leibniz figured out independently around the same time, which would cause one of the ugliest priority disputes in scientific history, but we'll get to that, was that you could find the instantaneous rate of change by looking at what happens as the interval of time shrinks towards 0. Not 0 itself, but the limit as it approaches 0. You're essentially asking, as I make my time window smaller and smaller and smaller, what value does the ratio of distance to time settle toward? That limiting value is the derivative. It's the instantaneous velocity. And the reverse process, if I know the velocity at every moment, can I add up all those tiny contributions to find the total distance traveled? That's integration. These two operations, differentiation and integration, are the twin pillars of calculus, and Newton showed that they're inverses of each other, two sides of the same coin. Now, here's why this matters so much for physics. Once you have calculus, you can write equations that describe how things change, not just how things are. You can write a law that says the rate of change of velocity equals the force divided by the mass. And that's Newton's second law, F equals ma, which we'll come back to. You can describe orbits, oscillations, fluid flow, heat conduction, anything that evolves over time. Calculus is the language of physics. Before Newton, physics was a collection of insights. After Newton, it became a mathematical system. And the light. Let's talk about the light, because it's such a beautiful experiment. Newton was interested in optics, the study of light, partly because of practical problems with telescopes. The best telescopes of the day used lenses, and they all suffered from chromatic aberration. You'd look at a star and see colored fringes around it, little rainbows at the edges, because the lens bent different colors by slightly different amounts. Everyone assumed this was a defect of the lens, something you could fix with better glass or a cleverer shape. Newton suspected something deeper, so he darkened his room at Woolsthorpe, actually bought a prism at a local fair, which is a charming detail, and let a thin beam of sunlight in through a small hole in the shutters. He passed the beam through the prism, and of course it spread out into a rainbow of colors on the opposite wall. This was well known. People had been playing with prisms for centuries. But here's what Newton did that was new. He took a second prism and passed just one color, say, the red portion of the spectrum, through it. And the red light came through the second prism, still red. It didn't spread out further. It didn't change. Then he took all the colors from the first prism and recombined them through a lens, and they came back together as white light. The conclusion was revolutionary. White light is not pure. It's a mixture. It's composed of all the colors, and the prism doesn't add color to the light. It separates what's already there. Each color has its own specific degree of refrangibility, its own angle of bending, and this meant chromatic aberration in telescopes wasn't a flaw you could engineer away with better lenses, because any lens that bends light will bend different colors differently. That's just what light does. So Newton, being Newton, didn't just identify the problem. He invented a solution. He designed a telescope that used a curved mirror instead of a lens to focus light, because reflection doesn't separate colors the way refraction does. The Newtonian reflector. It was a tiny little thing, about 6 inches long, but it worked beautifully, and the basic design is still used in telescopes today, including many of the largest observatory instruments in the world. But of course, the big one, the one that changed our entire understanding of the universe, was gravity. And here's where the famous apple comes in. Did an apple really fall on Newton's head? Almost certainly not on his head, no. But Newton himself told the story late in life to multiple people, including his friend William Stukeley, who recorded it. Newton said he was sitting in the garden at Woolsthorpe in a contemplative mood, and he saw an apple fall from a tree, and he began to wonder, why does the apple fall straight down? Why not sideways or upward? Why always toward the center of the earth? And then the crucial leap. Does this same force extend further? Does it reach up to the moon? Think about what a bold question that is. In the old Aristotelian framework, the earthly realm and the celestial realm were fundamentally different. Things fell down here because that was their nature. The moon moved in circles up there because that was its nature. Completely separate physics for the ground and the sky. But Newton asked, what if it's the same force? What if the same pull that brings the apple down is what keeps the moon in its orbit? Here's the way to think about it, And this is one of the most beautiful thought experiments in all of physics. Imagine you're standing on a very tall mountain, impossibly tall, above the atmosphere, and you throw a ball horizontally. It flies forward, but gravity pulls it down, so it curves and hits the ground some distance away. Now, throw it harder. It goes farther before it hits the ground because the Earth's surface is curving away beneath it. Throw it harder still, and it goes even farther. Now, throw it hard enough, and something magical happens. The ball is falling toward the Earth, but the Earth's surface is curving away at exactly the same rate. The ball falls and never hits the ground. It just keeps going around. That's an orbit. An orbit is just falling, perpetually, and missing. The moon is falling toward the Earth right now, every second of every day. It's just moving sideways fast enough that it keeps missing. And Newton didn't just have the idea, he did the calculation. He asked, if gravity weakens with distance, specifically, if it follows an inverse square law, getting 4 times weaker when you double the distance, then does the acceleration of the moon at its known distance match what you'd predict from the acceleration of the apple at the Earth's surface? He worked it out. And it did. It matched. The same force, the same law, governing both the falling apple and the orbiting moon. This was the unification that shattered the old division between terrestrial and celestial physics forever. There is one set of rules, and they apply everywhere. Now, Newton didn't publish any of this right away. That's important to understand about him. He was pathologically secretive. He worked out the calculus in 1665 and 1666 and told essentially nobody for 20 years. The gravity calculations he kept to himself. He went back to Cambridge after the plague, became Lucasian Professor of Mathematics in 1669, the same chair that Stephen Hawking would hold centuries later. And he lectured on optics, published his theory of light, and immediately got into a vicious dispute with Robert Hooke, who challenged his conclusions. Newton hated criticism with a fury that bordered on the pathological. The fight with Hooke was so unpleasant that Newton essentially withdrew from public scientific life for years. He retreated into private work on alchemy and biblical chronology, subjects he actually spent more time on than physics, which is a fascinating and slightly unsettling fact about the man who gave us the laws of motion. It took Edmund Halley, yes, the comet guy, to coax the masterwork out of Newton. In 1684, Halley visited Newton in Cambridge and asked him a question that had been stumping the best minds in London. If gravity follows an inverse square law, what shape would a planet's orbit be? Newton answered immediately, an ellipse. Halley was stunned and asked how he knew. Newton said he had calculated it years ago. Halley asked to see the proof. Newton rummaged through his papers, couldn't find it, and promised to redo it and send it along. What he actually did was far more than that. He sat down, and over the next 18 months or so, wrote the Philosophiae Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The Principia, published in 1687, largely at Halley's expense because Newton couldn't be bothered with the business side, and the Royal Society was broke from publishing a lavish book about fish. The Principia is, by almost any reckoning, the most important scientific book ever written. And what it contains is nothing less than a complete system of the world. That's actually the title of the third book inside it. The System of the World. And Newton means it literally. He's not just explaining one phenomenon or solving one puzzle. He's laying down a framework that accounts for the motion of everything, from a cannonball arcing over a battlefield to the moon sweeping around the Earth to the tides sloshing in and out twice a day. Everything moves according to the same rules, described in the same mathematical language. Nobody had ever done anything like that before. So let's walk through what's actually in there, because the ideas are so clean and so powerful that they're worth savoring. Newton opens with definitions and axioms, and then he gives you the 3 laws of motion. You've probably heard these stated in some form, maybe in a classroom, maybe on a poster somewhere. But let's really sit with them for a moment, because they're deeper than they sound. The first law says that an object at rest stays at rest, and an object in motion stays in motion in a straight line at constant speed, unless a force acts on it. Now, that sounds obvious to us, but remember, this was still a radical idea. For 2,000 years, Aristotle's framework had said that motion requires a cause, that things naturally slow down and stop unless something keeps pushing them. Galileo had started dismantling that idea with his thought experiments about frictionless surfaces and his concept of inertia. And now, Newton takes it and elevates it to a foundational law of nature. The natural state of things isn't rest. The natural state is whatever they're already doing. If a hockey puck is sliding across perfectly smooth ice, it will slide forever. It doesn't need a reason to keep moving. It needs a reason to stop. That shift in thinking, from why does it move to why does it change, is one of the most important conceptual revolutions in the history of human thought. The second law is the famous one, even if people don't always realize what it's really saying. Force equals mass times acceleration, F equals ma. 3 letters, and they encode an astonishing amount of reality. What this tells you is that force isn't about velocity, it's about the change in velocity. Push something, and you're not setting its speed, you're setting its acceleration. The heavier it is, the more force you need to accelerate it by the same amount. Think about pushing a shopping cart versus pushing a car. Same force, very different accelerations, because the masses are so different. And here's what's really powerful about this. If you know all the forces acting on an object and you know its mass, you can calculate exactly how it will accelerate at every instant. And if you know its acceleration at every instant, you can use calculus, Newton's own invention, remember, to figure out its velocity and position at every future moment. You can predict the future, not metaphorically, literally. Given the right information, Newton's second law lets you trace the trajectory of anything. The third law is the one people quote at parties. For every action, there's an equal and opposite reaction. And most people think this means something vague about karma or consequences, but Newton means something very specific. When you push on a wall, the wall pushes back on you with exactly the same force. When the earth pulls you down with gravity, you pull the earth up toward you with exactly the same gravitational force. The forces are equal. The reason you fall toward the earth and the earth doesn't noticeably move toward you is the second law. The earth is so fantastically massive that the same force produces an imperceptibly tiny acceleration on it, while it produces a very noticeable acceleration on you. The third law is what makes rocket engines work, by the way. A rocket doesn't push against the air. It doesn't need air. It throws exhaust gases out the back at tremendous speed, and by the third law, those gases push the rocket forward. That's why rockets work in the vacuum of space, which confused a lot of people for a surprisingly long time. Now, those 3 laws alone would be a monumental contribution. But Newton goes further. He takes his law of universal gravitation. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. And he combines it with the three laws of motion, and he just derives the solar system. He shows mathematically that Kepler's laws of planetary motion, which Kepler had painstakingly extracted from decades of observational data, are not separate empirical rules. They're consequences. They fall out automatically from Newton's laws. Kepler's first law, that planets move in ellipses with the sun at one focus. Newton proves it follows from inverse square gravity. Kepler's second law, that a planet sweeps out equal areas in equal times. Newton shows that's a consequence of any central force, not just gravity. Kepler's third law, the mathematical relationship between orbital period and distance. Derived. Done. 3 generations of astronomical observation, unified and explained by a single framework. And he doesn't stop with planets. He tackles the moon's motion, which is fiendishly complicated because the moon is being pulled not just by the Earth, but also by the sun, creating a 3-body problem that, as it turns out, has no exact analytical solution. Newton gets approximate answers that match observation remarkably well, and he's honest about the places where his calculations don't quite work out. Some of the lunar irregularities would take another century to fully resolve. He explains the tides as the result of differential gravitational pull from the moon and sun on different parts of the Earth's oceans. The side of the Earth closest to the moon gets pulled a little more than the center, and the center gets pulled a little more than the far side, so the oceans bulge on both sides. That's why you get 2 high tides a day instead of 1, which had been a genuine mystery. He explains the precession of the equinoxes, that slow wobble of Earth's axis that takes about 26,000 years to complete one cycle, as the gravitational effect of the sun and moon on Earth's equatorial bulge. He calculates the shape of the Earth itself, predicting that it should be slightly flattened at the poles and bulging at the equator due to its rotation, which was later confirmed by French expeditions, measuring the length of a degree of latitude at different locations. Think about what that means. One man, working essentially alone in his rooms at Cambridge, using mathematics he himself invented, explained the orbits of planets, the motion of the moon, the rhythm of the tides, the shape of the Earth, and the wobble of its axis, all from the same handful of principles. The scope of it is almost absurd. The Principia hit the scientific world like a thunderbolt. Not everyone understood it. The mathematics was dense, and Newton deliberately made it difficult, partly because he preferred the rigor of geometric proof over the algebraic methods he'd actually used to derive his results, and partly, some historians suspect, because he didn't want to make it too easy for lesser minds to nitpick. But those who could follow it recognized immediately that something fundamental had changed. The universe was no longer mysterious in the way it had been. It was a machine, and Newton had given you the operating manual. But here's the thing, and this is important for understanding how physics actually progresses. Newton's system had a philosophical problem at its heart that he knew about and couldn't solve. Gravity, in Newton's framework, acts instantaneously across any distance. The sun pulls on the Earth right now, across 93 million miles of empty space, with no delay and no mechanism. Newton himself found this deeply troubling. In a famous letter, he wrote that the idea of one body acting on another through a vacuum without any intermediary was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He was essentially saying, I know this looks like magic, and I don't like it either. But the math works. His phrase for this intellectual humility was hypotheses non fingo. I frame no hypotheses. He was saying, I can tell you exactly how gravity behaves mathematically with extraordinary precision, but I cannot tell you what gravity is or how it reaches across space. That question would remain unanswered for over 200 years, until a patent clerk in Switzerland started thinking about what would happen if you fell off a roof. But we're getting ahead of ourselves, because between Newton and Einstein, an enormous amount of physics happened, and some of it is just as fascinating as the headline acts. After the Principia, Newton became something of a national hero. He was elected president of the Royal Society in 1703 and held the position until his death in 1727, running it with an iron fist and using his influence to settle old scores, most notably with Leibniz, the German mathematician who had independently invented calculus. The priority dispute between Newton and Leibniz over who invented calculus first is one of the ugliest episodes in the history of science. Both men had legitimate claims. Newton had developed his method of fluxions first, in the mid-1660s, but hadn't published. Leibniz developed his version independently in the 1670s and published first, and his notation, the dx and dy and integral signs that we still use today, was frankly better than Newton's. But Newton accused Leibniz of plagiarism, and because Newton controlled the Royal Society, he essentially rigged the investigation into the dispute, probably even writing parts of the supposedly impartial report himself. The fight poisoned relations between British and continental mathematics for a century, and British mathematicians suffered for it, stubbornly sticking with Newton's inferior notation while the rest of Europe raced ahead using Leibniz's more flexible system. Newton died in 1727, and what he left behind was a picture of the universe as a vast clockwork mechanism, every part moving according to precise mathematical laws. If you could know the position and velocity of every particle in the universe at one moment, and if you could solve all the equations, you could in principle predict the entire future and reconstruct the entire past. This idea, determinism, would haunt physics and philosophy for centuries. The French mathematician Pierre-Simon Laplace, writing about a century after Newton, imagined a vast intellect that could know the state of every atom and calculate accordingly. Nothing would be uncertain, Laplace wrote, and the future, as the past, would be present to its eyes. This hypothetical being became known as Laplace's demon, and it represents the logical endpoint of Newtonian thinking pushed to its absolute limit. But the universe, it turns out, is stranger than even Newton imagined, and the first cracks in the Newtonian worldview didn't come from the heavens or from falling apples. They came from something much more humble, something you interact with every single day without thinking about it. They came from heat, from the simple, practical question of how to make a steam engine more efficient. And the person who started pulling on that thread was a French military engineer named Sadi Carnot, who in 1824 published a slim, elegant little book that almost nobody read at the time, a book about the motive power of fire, and what he discovered in those pages would eventually force physicists to accept something deeply unsettling, that the universe has a direction, a one-way arrow built into its very fabric, and that no amount of clever engineering can ever reverse it. Carnot was only 28 when he wrote Reflections on the Motive Power of Fire. He'd trained at the École Polytechnique in Paris, one of the finest scientific institutions in the world, and he'd watched with a mixture of fascination and national frustration as British steam engines transformed industry across the Channel. France was lagging behind, and Carnot wanted to understand, at the deepest possible level, what made steam engines work. Not any particular steam engine, He wanted to understand the fundamental principles governing all engines that convert heat into useful work. And here's what's remarkable about his approach. He didn't tinker with pistons and valves. He thought abstractly. He imagined an idealized engine, a perfect engine with no friction, no wasted heat, no imperfections of any kind. And then he asked a beautifully simple question. Even with this perfect engine, is there a limit to how much work you can extract from a given amount of heat? The answer was yes, and the reason was profound. Carnot realized that what drives an engine isn't heat itself. It's the flow of heat from a hot place to a cold place. Think of it like a waterfall. A waterfall can turn a mill wheel not because of the water, but because of the height difference. Water sitting in a lake at the top of a cliff has potential. Water sitting in a lake at the bottom has spent that potential. It's the drop that does the work. Carnot saw that heat works the same way. You need a temperature difference. Heat flows from hot to cold, and along the way, you can intercept some of that flow and convert it into mechanical work. But you can never convert all of it. Some heat must always be dumped into the cold reservoir. Always. No matter how clever your design, no matter how perfect your materials, you cannot build an engine that converts heat into work with 100% efficiency. It's not an engineering limitation. It's a law of nature. Now, Carnot didn't frame it in quite those terms. He was still working within the caloric theory of heat, which imagined heat as a kind of fluid that flows from hot bodies to cold ones. That theory turned out to be wrong. Heat isn't a substance. It's a form of energy, a manifestation of the random motion of atoms and molecules. But here's what's wild. Carnot's conclusions were right, even though his underlying model was wrong. The efficiency limit he derived, which depends only on the temperatures of the hot and cold reservoirs, holds up perfectly in modern physics. It's one of those rare cases where someone reached the correct destination by a slightly wrong road. Carnot died young, just 36, during a cholera epidemic in Paris in 1832. His work was almost entirely forgotten. But about a decade later, a British physicist named William Thomson, later Lord Kelvin, stumbled across Carnot's little book and recognized its importance. And around the same time, a German physicist named Rudolf Clausius was wrestling with the same questions. Between them, Kelvin and Clausius took Carnot's insights and built them into something monumental, the science of thermodynamics. Let's slow down here, because thermodynamics is one of those words that sounds intimidating, but really just means the study of heat and its relationship to energy and work. And the laws of thermodynamics, once you understand them, are stunningly simple to state, even if their consequences are vast. The first law is essentially conservation of energy. Energy can change form, from heat to work, from kinetic to potential, from chemical to electrical, but the total amount of energy in a closed system never changes. You can't create energy from nothing, and you can't destroy it. This was itself a major discovery, hammered out through the 1840s by several people working more or less independently. James Prescott Joule, a brewer's son from Manchester, did meticulous experiments showing that mechanical work could be converted into a precise, measurable amount of heat. He literally churned water with paddle wheels, driven by falling weights, and measured the tiny temperature increase. The German physician, Julius Robert von Meyer, arrived at similar conclusions from a completely different direction. He noticed that venous blood in the tropics was redder than in colder climates, and reasoned that the body needed to burn less fuel to maintain its temperature in hot environments, which led him to the idea that heat and mechanical work were interchangeable forms of the same thing. Hermann von Helmholtz, another German, provided the most rigorous mathematical formulation. By the 1850s, the scientific community had converged on a powerful idea. Energy is conserved. It's the bookkeeping rule of the universe. Every transaction balances. But the second law, that's the one that really changes everything. And this is Carnot's legacy, refined and sharpened by Clausius. The second law says that heat flows spontaneously from hot to cold, never the other way around. You can force heat to flow from cold to hot. That's what your refrigerator does. But it costs you energy to do it. And in the process, you always generate more heat than you moved. The total disorder of the universe always increases. Clausius invented a word for this, entropy. And entropy, once you grasp it, is one of the most profound concepts in all of physics. Think about it this way. If you drop a ball, it bounces, and each bounce is lower than the last, until eventually it just sits on the floor. The kinetic energy of the ball hasn't disappeared. The first law guarantees that. It's been converted into heat, into a tiny, imperceptible warming of the ball and the floor, the energy spread out among trillions of randomly jiggling molecules. And here's the thing. There's nothing in Newton's laws that prevents all those molecules from spontaneously coordinating their jiggling, pooling their energy back together, and launching the ball back into the air. Every individual molecular collision obeys Newton's laws perfectly in reverse. But it never happens. It never happens because the probability against it is so astronomically, incomprehensibly vast that you could wait for the entire age of the universe, and it still wouldn't happen. The second law of thermodynamics isn't like the other laws of physics. It's not a statement about what's impossible in principle. It's a statement about what's overwhelmingly, crushingly improbable. And in practice, that amounts to the same thing. This is the arrow of time. This is why you can remember yesterday, but not tomorrow. Why cream mixes into coffee but never unmixes. Why a broken egg doesn't reassemble itself. Newton's equations don't care which direction time runs. They work perfectly well forwards or backwards. But thermodynamics does care. It gives the universe a direction. Things fall apart. Order dissolves into disorder. And you can fight that tendency locally. You can build a house, grow a crystal, organize a library, but only by increasing disorder somewhere else by an even greater amount. The total entropy of the universe ratchets upward, always, relentlessly. Now, you might be lying there thinking, okay, that's philosophically interesting, but what does it have to do with the real world? And the answer is everything. The second law is arguably the most practically important law in all of physics. Every power plant, every engine, every biological cell operates under its constraints. When engineers design a jet engine or a nuclear reactor, the second law tells them the absolute maximum efficiency they can ever achieve, and it's always less than 100%. Always. The waste heat that comes out of your car's exhaust, the warmth radiating off the back of your laptop, that's the second law in action. You're paying the entropy tax. And here's something beautiful that connects back to our story. Remember Laplace's demon, that hypothetical intellect that could predict the entire future of the universe from perfect knowledge of the present? Thermodynamics was the first serious challenge to that vision, because even if you could somehow know the position and velocity of every particle, and that's already an absurd amount of information, the second law tells you that the universe is running down, spreading out, dissipating. The clockwork is unwinding. Newton gave us a universe of perfect, reversible, eternal motion. Thermodynamics said, no, things wear out. Energy degrades. The universe is aging. But thermodynamics also opened a door to something new, something that would eventually connect the behavior of trillions of invisible atoms to the large-scale properties we can see and measure. And the person who walked through that door most boldly was an Austrian physicist named Ludwig Boltzmann, working in the second half of the 19th century. Boltzmann was brilliant, passionate, and deeply troubled. He suffered from depression throughout his life, and he fought bitter intellectual battles against colleagues who didn't even believe atoms were real. In the 1870s and 1880s, that was still a genuine controversy. Many prominent physicists and chemists, particularly Ernst Mach and Wilhelm Ostwald, argued that atoms were just convenient fictions, useful for calculations, but not actual physical entities. Boltzmann believed they were real, and he staked his career on it. What Boltzmann did was take the second law of thermodynamics and explain it from the bottom up. He showed that entropy isn't some mysterious cosmic tendency. It's statistics. It's probability. If you have a box full of gas molecules, there are astronomically more ways for those molecules to be spread out evenly than there are ways for them all to be huddled in one corner. So a gas expands to fill its container, not because some force pushes it, but because the expanded state is overwhelmingly more probable than the compressed one. Entropy increases because systems naturally evolve toward their most probable configurations. That's it. That's the deep secret of the second law. Boltzmann expressed this with an equation so important, it's carved on his tombstone. S equals K log W. Entropy equals Boltzmann's constant times the logarithm of the number of microstates. It's a bridge between the microscopic world of atoms and the macroscopic world of temperature and pressure and heat. It's one of the most elegant equations in physics, and it was fiercely controversial in its time. Boltzmann's life ended tragically. In 1906, while on vacation with his family near Trieste, he took his own life. He was 62. Some historians believe the relentless attacks on his work contributed to his despair, though his depression had deeper roots than any scientific dispute. The bitter irony is that within just a few years of his death, the reality of atoms was confirmed beyond any doubt by Einstein's 1905 paper on Brownian motion and by Jean Perrin's meticulous experiments that followed. Boltzmann was vindicated, but he never knew it. And speaking of Einstein, that 1905 paper on Brownian motion was just one of 4 extraordinary papers he published that year, any one of which would have made a career. The year 1905 is sometimes called Einstein's annus mirabilis, his miracle year, and what happened in those 12 months represents one of the most astonishing bursts of creative genius in the history of human thought. Einstein was 26 years old, working as a patent clerk in Bern, Switzerland, evaluating applications for electromagnetic devices. He had no academic position, no laboratory, no research assistants. He had a desk, a pen, and a mind that saw deeper into the structure of reality than anyone since Newton. And the first of those 4 papers dealt with something that would have made Boltzmann weep with joy. It dealt with light, and with the strange, grainy quantum nature of energy itself. And it began with a puzzle about something called black-body radiation. And to understand why that puzzle mattered so much, you need to picture something simple. Imagine heating a piece of metal. You've seen this. You take an iron poker and stick it in a fire, and at first it just gets hot. You can feel the heat radiating off it, but it looks the same. Then it starts to glow a dull red, hotter still, and it turns orange, then yellow. Then, if you could get it hot enough, it would glow white, even bluish white. Every object does this. The color of the glow depends only on the temperature, not on what the object is made of. Iron, ceramic, tungsten, it doesn't matter. At the same temperature, they all glow the same color. Physicists in the late 1800s were obsessed with understanding this because it seemed like it should be straightforward. You have classical physics, Maxwell's beautiful equations describing electromagnetic radiation, and you have thermodynamics describing heat and energy. Surely you could combine the two and predict exactly how much light at each frequency a hot object should emit. And they tried. Lord Rayleigh and James Jeans worked out the classical prediction, and it matched reality pretty well at low frequencies, the long, lazy infrared wavelengths. But at higher frequencies, shorter wavelengths, the prediction went catastrophically wrong. Classical physics said that as you moved to higher and higher frequencies, the energy radiated should increase without limit. A hot object should blast out infinite energy in the ultraviolet and beyond. Obviously, that doesn't happen. Your fireplace doesn't kill you with a burst of gamma rays every time you light a fire. This embarrassing failure got a dramatic name, the ultraviolet catastrophe. And it wasn't just a minor discrepancy. It was classical physics saying something that was flatly, absurdly wrong. In 1900, Max Planck found a way to fix the math. Planck was a conservative, careful physicist in Berlin, not at all the revolutionary type. He was the kind of man who wanted everything to fit neatly into the existing framework. But he couldn't make the numbers work unless he introduced a strange assumption, that energy wasn't emitted continuously, the way classical physics assumed, but in tiny discrete packets, little indivisible chunks. He called them quanta. The size of each quantum was proportional to the frequency of the light, higher frequency, bigger quantum. And the constant of proportionality was a new fundamental number, an incredibly tiny number, which we now call Planck's constant, h. It's about 6.6 times 10 to the negative 34 joule seconds. Absurdly small. But it fixed the blackbody spectrum perfectly. Here's the thing, though. Planck himself didn't really believe it. He thought it was a mathematical trick, a convenient fiction that happened to give the right answer. He spent years trying to derive the same result without the quantum assumption. He couldn't. But he also couldn't bring himself to accept that energy was truly granular at the deepest level. That step, taking the quantum seriously, treating it as physically real, that was Einstein. Einstein's first 1905 paper argued that light itself comes in quanta, not just the emission process, not just a mathematical convenience, but the light itself. It's made of particles, each carrying energy equal to Planck's constant times the frequency. He used this idea to explain the photoelectric effect, a puzzling phenomenon where light shining on a metal surface kicks out electrons. The weird thing about the photoelectric effect was that the energy of the ejected electrons didn't depend on how bright the light was. It depended on the color, the frequency. Dim ultraviolet light could kick out energetic electrons, but no amount of bright red light could kick out any electrons at all. Classical wave theory couldn't explain this. But if light comes in packets, and each packet's energy depends on frequency, then it makes perfect sense. A single ultraviolet photon carries enough energy to knock an electron free. A red photon doesn't, no matter how many red photons you throw at the surface. This was radical. For a century, the wave nature of light had been established beyond question. Thomas Young's double-slit experiment, Maxwell's equations, all of it pointed to light being a wave. And now Einstein was saying it's also a particle, not instead of a wave, also a particle. Both at once. That's strange. That's deeply, fundamentally strange, and physicists would spend the next 20 years wrestling with just how strange it was. But Einstein wasn't done with 1905. Not even close. The Brownian motion paper we already talked about. That was the one that vindicated Boltzmann, proving atoms were real by showing that the jittery dance of pollen grains in water was caused by molecular bombardment. The third paper was on special relativity, and this is the one that changed everything about how we think about space and time. The problem Einstein was chewing on had to do with light again, but from a different angle. Maxwell's equations predicted that electromagnetic waves, light, travel at a specific speed, about 300,000 kilometers per second. But speed relative to what? In Newtonian mechanics, speed is always relative. You're sitting still right now, but relative to the sun, you're moving at about 30 kilometers per second. So when Maxwell's equations say light travels at c, what's the reference frame? Physicists assumed there must be a medium, a substance filling all of space, called the luminiferous ether, and that light's speed was relative to this ether. In 1887, Albert Michelson and Edward Morley ran a brilliant experiment to detect Earth's motion through this ether. They split a beam of light, sent the two halves in perpendicular directions, and looked for a difference in speed that would reveal which way Earth was moving through the ether. They found nothing. No difference. No ether wind. The speed of light was the same in every direction, regardless of how the Earth was moving. This result baffled everyone. Various physicists proposed fixes. Maybe objects contract slightly in the direction of motion. Maybe the ether gets dragged along with Earth. These were patches, band-aids. Einstein did something far more audacious. He took the experimental result at face value and asked, what if the speed of light really is the same for all observers, no matter how they're moving? What if that's not a problem to be explained away, but a fundamental law of nature? From that single postulate, combined with the principle that the laws of physics are the same in all inertial reference frames, Einstein derived special relativity, and the consequences are breathtaking. If the speed of light is the same for everyone, then something else has to give. And what gives is our intuitive sense of space and time. Time passes at different rates for observers moving at different speeds. Lengths contract in the direction of motion. Two events that are simultaneous for one observer might not be simultaneous for another. These aren't optical illusions or measurement errors. They're real. The fabric of reality itself behaves this way. And then there's the fourth paper, the short one, almost an afterthought. Just 3 pages. That's the one where Einstein showed that mass and energy are equivalent. E equals mc squared. Energy equals mass times the speed of light squared. And because c squared is an enormous number, about 9 times 10 to the 16 in metric units, even a tiny amount of mass corresponds to a staggering amount of energy. This is the equation that would eventually explain how the sun shines, how nuclear reactors work, and yes, how nuclear weapons are possible. But in 1905, all of that was decades away. Einstein was just following the math where it led. Think about what happened in that single year. A 26-year-old patent clerk, working in his spare time, published 4 papers that collectively established the reality of atoms, launched quantum theory, overthrew Newtonian absolute space and time, and revealed the equivalence of mass and energy. It's almost absurd. And the physics community took a while to catch up. The relativity paper, in particular, was not immediately recognized for what it was. It took years for the full implications to sink in. But Einstein wasn't finished. Special relativity dealt with observers moving at constant velocities, inertial frames. It said nothing about acceleration, nothing about gravity. And Einstein knew that gravity was the big unsolved problem. Newton's law of gravitation worked beautifully for predicting orbits and trajectories, but it had that old philosophical problem: action at a distance. The sun pulls on the Earth. But how? Through what mechanism? Newton had famously refused to speculate. Einstein refused to leave it alone. The key insight came to him in 1907, and he later called it the happiest thought of his life. He imagined a person in free fall, someone falling off a roof, say. During the fall, that person would feel weightless. They wouldn't feel gravity at all. Einstein realized that this meant acceleration, and gravity are fundamentally indistinguishable. If you're in a closed box and you feel a force pulling you toward the floor, you can't tell whether the box is sitting on the surface of a planet or being accelerated upward by a rocket. This is the equivalence principle, and it became the foundation of general relativity. It took Einstein 8 more years of grueling mathematical work to turn that insight into a complete theory. He had to learn entirely new mathematics, Riemannian geometry, tensor calculus, and he struggled, made wrong turns, published incorrect equations, and nearly lost the race to the mathematician David Hilbert, who was working on the same problem from a purely mathematical direction. In November 1915, Einstein finally presented the correct field equations of general relativity to the Prussian Academy of Sciences. And what those equations say is extraordinary. Gravity isn't a force in the Newtonian sense. It's the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. The Earth doesn't orbit the Sun because some invisible force is pulling on it. The Earth is following the straightest possible path through space-time that has been curved by the Sun's mass. It's rolling along the contours of a geometry that the Sun has shaped. And general relativity made predictions that differed from Newton. It predicted that light itself should be bent by gravity, that a beam of starlight passing near the Sun should be deflected slightly. In 1919, Arthur Eddington led an expedition to observe a total solar eclipse off the west coast of Africa, on the island of Principe. During the eclipse, when the Sun's glare was blocked, he photographed the stars near the Sun's edge and measured their apparent positions. They had shifted by almost exactly the amount Einstein predicted. When the results were announced, Einstein became the most famous scientist in the world overnight. Headlines everywhere. The Newtonian universe, unchallenged for over 2 centuries, had been superseded. But here's what's beautiful. Newton wasn't wrong. Newton was a special case. In the limit of weak gravity and low speeds, Einstein's equations reduced to Newton's. The old theory is contained within the new one, like a small circle inside a larger circle. That's how physics progresses. Not by demolishing what came before, but by revealing it as an approximation of something deeper. And while Einstein was reshaping gravity and space-time, quantum theory was evolving in directions that even Einstein found disturbing. Niels Bohr had taken Planck's quantum idea and applied it to the atom. In 1913, Bohr proposed a model of the hydrogen atom where electrons orbit the nucleus only at specific quantized energy levels. They can't spiral inward continuously the way classical physics predicted. They jump between orbits, absorbing or emitting a photon of exactly the right energy. It was ad hoc, it was strange, but it worked. It predicted the spectral lines of hydrogen with stunning accuracy. Through the 1920s, a new generation of physicists, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, Wolfgang Pauli, built quantum mechanics into a complete mathematical framework. And what emerged was a picture of reality that defied every intuition humans had ever developed. Particles don't have definite positions until you measure them. They exist in superpositions of multiple states simultaneously. The act of measurement itself changes the outcome. And there's a fundamental limit to what you can know. Heisenberg's uncertainty principle says you cannot simultaneously know both the exact position and exact momentum of a particle. Not because your instruments aren't good enough, but because the universe itself doesn't have definite values for both at the same time. Einstein hated this. He spent the last 30 years of his life arguing against the completeness of quantum mechanics, famously declaring that God does not play dice. He and Bohr had legendary debates. At the Solvay conferences in Brussels, Einstein would construct elaborate thought experiments designed to show that quantum mechanics must be incomplete, and Bohr would stay up all night finding the flaw in Einstein's argument. Every time, Bohr won. Quantum mechanics survived every attack. And here's what's remarkable. Both men were partly right. Quantum mechanics, as formulated in the 1920s, is the most precisely tested theory in the history of science. Its predictions have been confirmed to 12 decimal places. It underlies every piece of modern technology. Semiconductors, lasers, MRI machines, the device you might be listening to right now. But whether it's the final word on reality, whether it's complete in the way Bohr believed, that question is still open. Still genuinely, honestly open. And that's not a failure of physics. That's actually one of the most fascinating things about it. Because quantum mechanics works. It works better than any theory ever constructed. And yet the people who use it every day still argue about what it means. Not what it predicts, mind you. The predictions are settled. But what it says about the nature of reality itself, that's a different story entirely. Let's sit with that for a moment, because it's worth understanding just how strange the situation is. You have a mathematical framework that lets you calculate, with absurd precision, the probability of any quantum event. You can predict the energy levels of atoms, the behavior of subatomic particles, the exact wavelength of light emitted when an electron drops from one orbital to another. The standard model of particle physics, which is built on quantum mechanics, predicted the existence of the Higgs boson decades before it was found at CERN in 2012. The magnetic moment of the electron, a quantity that describes how it interacts with magnetic fields, has been calculated using quantum electrodynamics to something like 12 significant figures, and the experimental measurement matches. 12 significant figures. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. No other theory in any field of human knowledge has ever achieved that level of agreement between prediction and observation. And yet, if you ask a room full of physicists what quantum mechanics actually tells us about the world, not the math, but the reality behind the math, you'll get genuinely different answers. There's the Copenhagen interpretation, which was essentially Bohr's view and became the orthodox position for most of the 20th century. It says that the wave function, that mathematical object that describes all the possible states a particle could be in, doesn't represent something physically real. It's a tool for calculating probabilities, nothing more. When you make a measurement, the wave function collapses and you get a definite result. But asking what the particle was doing before you measured it, that's not a meaningful question. The measurement is what brings the result into existence. Then there's the many worlds interpretation, proposed by Hugh Everett in 1957. Everett was a graduate student at Princeton, working under John Wheeler, and his idea was radical. He said the wave function never collapses. Instead, every time a quantum measurement occurs, the universe splits. Every possible outcome happens, but in separate, non-communicating branches of reality. You measure an electron's spin and get up. In another branch, another version of you got down. Both outcomes are equally real. There's no collapse, no special role for measurement, no randomness, just an endlessly branching tree of parallel realities. When Everett first proposed this, almost nobody took it seriously. Bohr apparently found it almost offensive. Everett eventually left physics entirely, went into defense work, and died in 1982 without ever seeing his interpretation gain the respect it has today. Because today, many worlds has a significant following among theoretical physicists and cosmologists. It's mathematically clean, it solves the measurement problem, and it takes the wave function seriously as a description of reality. The cost, of course, is that you have to accept an essentially infinite number of parallel universes, which is, well, it's a lot to take in. There are other interpretations too. David Bohm proposed a pilot wave theory in 1952, where particles do have definite positions at all times, guided by a wave that carries information about the entire system. It reproduces all the predictions of standard quantum mechanics, but restores determinism. Everything has a definite state. We just can't access all the information. Einstein actually liked Bohm's approach, though it never became mainstream, partly because it requires a kind of instantaneous connection between distant particles that made many physicists uncomfortable. There's also the decoherence program, which explains how quantum superpositions become effectively classical through interaction with the environment, how the weirdness of the quantum world gets washed out at larger scales, which is why you never see your coffee cup in two places at once. Decoherence is real physics, experimentally confirmed, and it helps explain the boundary between quantum and classical, but it doesn't fully resolve the measurement problem by itself. Here's the thing, though, and this is what I want you to appreciate as you're lying there, maybe drifting a little. The fact that these interpretive questions remain open doesn't mean physics is stuck. It means physics has reached a place where the questions themselves have become extraordinarily deep. We're not arguing about what happens. We're arguing about what reality is. And that's a different kind of question than anything Newton or even Einstein had to face. But let's come back to the story, because the 20th century wasn't done with physics yet, not by a long shot. While quantum mechanics was being debated and refined, another revolution was unfolding, one that would connect the very large to the very small in ways nobody anticipated. And it started with Einstein's general relativity. Remember, general relativity describes gravity as the curvature of space-time. Massive objects warp the fabric of space and time around them, and other objects follow the curves. When Einstein published his field equations in 1915, they were immediately applied to the biggest system anyone could think of, the universe itself. In 1922, a Russian mathematician named Alexander Friedmann found solutions to Einstein's equations that described a universe that was expanding or contracting, not static, not fixed, dynamic. Einstein didn't like this. He actually introduced a term into his equations called the cosmological constant, specifically to keep the universe static, because that's what everyone assumed it was. He later called that his greatest blunder. And then, in 1929, Edwin Hubble, working at the Mount Wilson Observatory in California, using what was then the most powerful telescope in the world, discovered that distant galaxies are moving away from us, and not just moving away, but moving away faster the farther they are. The universe is expanding. Friedmann had been right. Einstein's equations, without the cosmological constant, naturally predicted exactly this. The universe had a beginning, a moment when everything was compressed into an unimaginably dense, hot state. We call it the Big Bang, a name that was actually coined as a joke by Fred Hoyle, a British astronomer who didn't believe in it, during a BBC radio broadcast in 1949. The name stuck anyway. Now, here's where things get really interesting. The Big Bang isn't just an idea, a speculation, a philosophical proposition. It's a theory with precise, testable predictions. And one of the most beautiful confirmations came in 1965, almost by accident. Two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to calibrate a large horn antenna for satellite communications. They kept picking up a faint microwave signal, a persistent hiss that they couldn't get rid of. They checked everything. They even cleaned pigeon droppings out of the antenna, thinking that might be the source. It wasn't. The signal was coming from everywhere in the sky, uniformly, at a temperature of about 2.7 degrees above absolute zero. What they had found, without realizing it at first, was the cosmic microwave background radiation, the afterglow of the Big Bang itself, the cooled remnant of the radiation that filled the universe when it was only about 380,000 years old. It had been predicted theoretically by Ralph Alpher and Robert Herman in 1948, but Penzias and Wilson didn't even know about that prediction when they stumbled onto it. They won the Nobel Prize. And that faint hiss, that barely detectable whisper of microwaves, is one of the most profound pieces of evidence in all of science. It tells us the universe has a history. It had a beginning. It evolved. And here's where the story of physics starts to fold back on itself in the most beautiful way. Because to understand what happened in the first moments after the Big Bang, the first fractions of a second, when the universe was unimaginably hot and dense, you need quantum mechanics. You need particle physics. The physics of the very small becomes essential for understanding the origin of the very large. General relativity describes the large-scale structure of the universe, how space-time curves, how galaxies form, how the expansion proceeds. Quantum mechanics describes the particles and forces that filled that early universe. And the great unfinished project of physics, the thing that has occupied some of the most brilliant minds of the last 50 years, is figuring out how to combine them. Because right now, general relativity and quantum mechanics are, in a deep mathematical sense, incompatible. They work beautifully in their own domains. But when you try to apply both at the same time, at the center of a black hole, say, or at the very instant of the Big Bang, where you have extreme gravity and extreme quantum effects simultaneously, the math breaks down. You get infinities. You get nonsense. This is the problem of quantum gravity. And it's the biggest open problem in fundamental physics today. String theory is one approach. It proposes that the fundamental constituents of reality aren't point particles, but tiny vibrating strings, and that their different modes of vibration give rise to all the particles and forces we observe. It's mathematically rich, extraordinarily elegant, and so far, it hasn't made a prediction that can be tested with current technology. Loop quantum gravity is another approach, which tries to quantize spacetime itself, breaking it into discrete chunks at the smallest possible scale, the Planck scale, about 10 to the minus 35 meters, a distance so small that it makes a proton look like a galaxy by comparison. Neither approach has won. The problem remains open, and that's okay. Because if the history of physics teaches us anything, and we've covered a lot of that history tonight, it's that the biggest breakthroughs often come after long periods of confusion and frustration. Newton sat with the problem of planetary motion for 20 years before the Principia. Einstein spent 8 years struggling from special relativity to general relativity. Boltzmann died before his ideas were accepted. The pattern, over and over, is that the universe is more subtle than we expect, and understanding it requires not just intelligence, but patience, persistence, and sometimes a willingness to let go of assumptions that feel as solid as the ground beneath your feet. Think about the arc of what we've covered tonight. We started with people who simply noticed that things fall, that fire is hot, that the stars move in patterns. We watched as the Greeks began asking why, as Archimedes found mathematical laws hiding inside the physical world, as medieval scholars quietly laid the groundwork for the science of motion. We saw Galileo point his telescope at the sky and change everything, and Newton pull the whole universe into a single mathematical framework. We watched thermodynamics reveal the deep connection between heat and motion, and Boltzmann show that the laws of thermodynamics emerge from the random dance of atoms that most of his colleagues didn't even believe in. We followed Einstein as he reimagined space and time, bent the geometry of the universe, and showed that mass and energy are the same thing. And we watched quantum mechanics shatter every intuition about how reality works at its most fundamental level. And through all of it, through every revolution, every breakthrough, every bitter debate, there's been this thread, this continuous thread of human curiosity. People lying awake at night, just like you are now, wondering how things work, wondering why the world is the way it is, wondering whether the rules they've found are the final rules or just approximations of something deeper. That's what physics is, really. It's not the equations, though the equations are beautiful. It's not the technology, though the technology changes the world. It's the wondering. It's that feeling you get when you look up at the night sky and realize that the light hitting your eyes left those stars years ago, decades ago, centuries ago, that you're literally looking back in time. It's the quiet astonishment of learning that you, right now, lying wherever you are made of atoms that were forged inside stars that exploded billions of years ago. The carbon in your bones, the iron in your blood, the oxygen you're breathing, all of it was cooked in the nuclear furnaces of ancient stars and scattered across space when those stars died. You are, in the most literal and scientifically precise sense, made of stardust. And the laws that govern those stars, the gravity that pulls them together, the nuclear forces that make them shine, the quantum mechanics that determines which elements they produce. Those are the same laws that govern you, the same physics. From the largest structures in the observable universe down to the smallest particles inside your atoms, it's one continuous story, one set of rules, still being discovered, still being refined, still full of mysteries. So let that settle over you. Let the weight of it be gentle, not heavy. The universe is strange and beautiful and not fully understood, and that's not a source of anxiety. It's a source of wonder. There are questions left to answer. There are discoveries waiting to be made. And somewhere right now, someone is lying awake, staring at a problem on a chalkboard or a computer screen, and they're about to see something no one has ever seen before. The story of physics isn't over. It's still being written. But you don't need to write it tonight. Tonight, you can just rest in the knowledge that the universe is comprehensible, imperfectly, incompletely, but genuinely comprehensible. That the same curiosity that drove Archimedes to leap out of his bath, and Galileo to build his telescope, and Einstein to imagine riding a beam of light, that curiosity is the most human thing there is, and it's still alive. It'll be there tomorrow. For now, just let the story settle. Let your thoughts soften, and let the quiet hum of the universe, that faint cosmic background radiation, that ancient whisper from the beginning of everything, carry you gently, gently into sleep.